Hello everyone, welcome to the another lecture of chemical bonding class 11. Myself Suman Singh. So in the last class we have discussed about the Vesper theory, right? So now in today's class we will discuss about hybridization. So what is hybridization? Hybridization is you have also learned in in your biology, right? So this is same as that one, but here we will talk about the atomic orbital. Okay, so hybridization is just what we can say, it is an intermixing. Okay, so how we can define this hybridization? We can define like this: the intermixing of the intermixing of pure atomic orbital of an atom having nearing energy to give a set of equal number of identical hybrid orbital of the same energy is called hybridization. Okay, or we can also define like this: the intermixing of atomic orbital of slightly different energies to form a more symmetrical orbital of equivalent energy is called hybridization. Okay, so there are some lots of definitions are there to define this hybridization. So first of all, we will see rules for, before going to the rules for hybridization, we will see what are the conditions of hybridization. Okay, so first, the first condition for hybridization is only valence shell orbital hybridize. Okay, in hybridization only valence shell hybrid or valence shell orbitals will hybridize. Okay, now next is comparable energy orbital take parts in hybridization. Okay, now next is only orbitals undergo hybridization, not the electrons. We will discuss about this in these rules for hybridization also. And one more thing is half filled, fully filled or empty orbitals may hybridize, right? And the last one is excitation of electron is not necessary. So this was about the conditions for hybridization. Now we will see rules for hybridization. There is same conditions or rule. So first rule, because I am explaining you from here, because it is very written here very in a simple way and very clearly, right? As you can see, the first rule is atomic orbital of an atom can intermix. Okay, only the atomic orbital of an atom can intermix, right? Now next is atomic orbital have a nearing energy can intermix. Means what? The atomic orbital whose energies are almost same or nearly same, they can intermix to form hybrid orbitals. Okay, now next is vacant, half filled or completely filled atomic orbital can intermix to form hybrid orbital. If it is a half filled, or if it is a vacant, or if it is a completely filled, in both the three cases the atomic orbital can intermix to form hybrid orbital. Okay, now next is the number of hybrid orbital formed will be equal to the number of atomic orbital intermix. Means number of hybrid orbital will be equal to number of atomic orbital, number of atomic orbital mixed, right? Now next is hybrid orbital are identical in shape and have a same energy, but the different in their orientation in space. Means what? The after the intermixing of atomic orbital, when they will form a hybrid orbital, at that time their shape and energy will be same, but when we talk about its orientation in space, it will be different. Okay, we will see the example also, some of the example how their orientations are different. We will see that. Okay, so what we have seen that hybrid orbital are identical in shape, okay, and have a same energy but different in orientation, different orientation in space. Okay, now next is electrons are redistributed in this orbital. The electrons are distributed in this orbital following Hund's rule and Pauli exclusive principle. So I hope we have learned this Hund's rule and Pauline's exclusive principles in atomic structure, right? So that rule, whatever the rule is there, Hund's rule and Pauling exclusive principle, according to that rule only the electrons will be redistributed in the hybrid orbital. Okay, it is not like that it will not follow the Hund's rule or Pauli exclusive principle. It will follow the same rule when they will redistribute the when there will be a redistribution of electron in the hybrid orbital. Okay, now Next, always remember that atomic orbital only participate in hybridization, not the electrons. Okay, electrons will not participate in hybridization, only the atomic orbital will participate. Okay, now next is hybrid orbital form sigma bond. Okay, unhybrid orbital form pi bond. Okay, always remember that the hybrid orbital will never form a sigma bond. Okay, it will, which one, if you will see in any molecules or in any compound, if there is a sigma, if there is a pi bond, then always remember that that pi bond is formed due to unhybrid orbitals. Okay, not with the hybrid orbital, because hybrid orbital always form what, sigma bond. Okay, now next is the molecule has a regular geometry. We will see about the geometries also. Okay, and when hybrid orbital contains a shared pair of electron, if one or more lone pair of electron is in the valence shell, molecule will show distorted geometry. Okay, we will talk about this. Okay, so what is written here is, you can see that the molecule will have a regular geometry. Okay, but when the hybrid orbital will contains a lone pair of electrons, okay, at that time the valence shell molecules will show a distorted geometry. Okay, we will see with the example also. Now next is, each hybrid orbital have a two lobes. Okay, each hybrid orbital will have a two lobes. One is larger and the another one will be smaller. Okay, and the bond will be formed from a larger lobe. Always remember that, suppose this is an, let me draw here, suppose this is one orbital is there, right? So when this orbital will convert into a hybrid orbital, it will look like this. One will be a smaller lobe, as you can see, one will be a smaller lobe and another will be a bigger lobe, larger lobe. So this larger lobe will participate in bonding. Okay, as you can see here, each hybrid orbital each hybrid orbital will have two lobes. One is large and another one is smaller, as you can see, like this. Okay, this one is smaller and this one is large lobe, right? And the bond will be formed by larger lobe. This will form a bond. Okay, we will see that. Okay, now next is, last one is, the hybrid orbital are oriented in space as far as possible. Okay, the hybrid orbital which will be formed, this way they will their orientation in space will be as far as apart as possible. And why? And thus they will help in determining the shape and geometry of the molecule. Okay, so we will see in detail about this. So I hope you have got some idea about the hybrid orbital. Okay, so now next is overlapping. What is the difference between overlapping and hybridization? This is also a very important topic, because it will make you clear, it will give a clear idea about the hybridization. As you can see, overlapping is what, it occurs between the orbital of two atoms. Okay, right? One atom is this and this, and one atom is this. They will overlap like this, and they will overlap like this, right? But when we talk about the hybridization, it occurs among the orbital of the same atom. Means overlapping is between the different atom. Okay, one atom is this, another atom is this, but when we talk about the hybridization, it will be with the same atom. Okay, now next is, only half filled orbital participate in in overlapping. Okay, but here any type of orbital can participate. Okay, here when the orbital is half filled like this, suppose this is an s orbital, and if it is half filled, then only if one more s orbital is there which is also half filled, at that time they will overlap with each other, right? They will overlap with each other like this, right? Or if we talk about the p orbital, suppose this is a p orbital here, this is half filled, and this is also a p orbital here, this is half filled. So what they will do, they will overlap each other, right? So this is called overlapping. But in hybridization, the any type of orbital can participate. Okay, now next is, when we talk about the overlapping, it occurs during the bond formation and bond form and it occur on during the bond formation, bond form after hybridization. Okay, but here in the process just before overlapping. Okay, hybridization is overlapping is done after hybridization. Okay, but when we talk about the hybridization, it occurred before overlapping, as you can see here. Okay, now next is, orbital of different energy may participate in excited state. means what? In overlapping, the orbital of different energy may participate, but in the hybridization, it may take place in the ground or excited state. Okay, suppose you can see the example in ground state, ns3 ncl3 ps3 or pcl3 is given here. Okay, and the hybrid orbital are and hybridized orbital are formed, and here molecular orbital are formed. Okay, when there will be an overlapping, at that time MOT, molecular orbital, will form, and when there will be hybridization, there will, at that time hybrid orbital will form, right? Now next is type of hybridization. So there are different type of hybridization is there, just like sp hybridization, sp2 hybridization, sp3 hybridization. Okay, when hybridization will involve only s and p orbital, at that time there will be a three type of hybridization. Okay, one will be sp, sp2 and sp3. Okay, now again, when the hybridization will involve s, p and d, both three of them, at that time the hybridization will be sp3d. Okay, and dsp2. Okay, after that there will be uh, sp3d2. Okay, and after that there will be d2sp3. Okay, and after that there will be sp3d3. Okay, so when the hybrid orbitals will when the hybridization is involving s and p orbital, at that time there will be a three type of hybridization will be. One will be sp, another one will be sp2, and the third one will be sp3. Okay, but when the hybridization will involve this both s, p and d, at that time there will be a five type will be. First one is sp3 d hybridization, d sp2 hybridization, and after that sp3 d2 hybridization, and d2 sp3 hybridization, and sp3 d3 hybridization. Okay, so one by one we will see, because it is very important for your exam also. So first one is sp hybridization. Okay, so here everything is given, we will see from here only, because here you can see in sp3 hybridization, or we can say when we talk about the sp hybridization, here first of all let me draw you, and here you see that here will be one s orbital like this, there will be one s orbital. Okay, and it will combine with one p orbital. Okay, here it will combine with one 2p orbital. Okay, so this 2p orbital, and it will form what? It will form a hybrid orbital like this, which is called 2sp2, right? So here you can see, in this is the small lobe, what I have told you previously, there will be a two lobe, one lobe will be bigger and another lobe will be smaller, right? And always remember that this is what, this is unhybrid, but when it will hybridize, it will form like this. Okay, one lobe will be smaller, another lobe will be bigger. Okay, now next is when these two will combine, always remember that when they will combine, suppose it will combine like this, it will combine like this. Okay, it will combine like this, is called what? This is sp, and this is also sp, right? And suppose one take the example of bcl3, so be, here is cl, so the angle will be, regular bond angle will be 180. Always remember that in sp hybridization the regular bond angle is 180. Okay, and suppose if we are taking here, suppose this is s, and at that time px, it is combining with ps, so the direction of the bond, or we can say the hybridization, will be along x-axis. Okay, this is what? X-axis, right? X-axis. If there is s and it is combining with py, so at that time it will be along y-axis, right? And if it is along, it is combining with pz, sorry, if it is p from pz, at that time it will be along z-axis. Okay, now next is, I hope you have got some idea, right? So one more example I will give you. Suppose this is our s. Okay, and this is our p, so they will combine. When they will hybridize, they will form like this, one small lobe one bigger lobe, and after that they will combine, the two will combine each other to form like this. It will form like this word here, this is sp, and here also this is sp, and the regular bond angle, this one or this one is 180, okay, rba, which is called regular bond angle. So I hope you have got some idea, right? So we will see from here. Here you can see in sp hybridization, one s and one p orbital intermix to form what? sp3 hybrid orbital, okay. And this process is called sp hybridization, okay. Now in sp hybridization, in sp hybrid orbital of equivalent shape and energy, when we talk about the sp hybrid orbital, they are of equivalent shape and energy and arrange in a straight line, okay. Always remember that whatever the product, whatever the it will be like this. We have taken the, we have seen the example of bcl3, right? So as you can see, cl will be here and then one cl will be here, right? So this is 180. So as you can see, this is what linear shape, right? So this will be in a straight line, and which is a linear shape, right? And with an angle of 180, as we have discussed, right? Now each sp hybrid orbital will have 50% s character, okay, and 50% p character, okay. So always remember that the character shape, sp molecule type will be ab2. When we talk about the molecule type, a molecule type will be a b2 or ab, okay. And the character, when we talk about this character, there will be 50% s character and 50% p character, okay. And that when we talk about the geometry, it will be linear, okay. Linear geometry, it will be linear geometry, okay. And when we talk about the regular bond angle, it will be, regular bond angle will be 180, okay, 180 degrees, right? Now next is some of the example I hope you have understood after this, right? Now next, some of the example, as you can see, of sp2 hybridization is given here, okay. So first is example of BeH2. So here central atom is what? Be, right? Here in central atom is Be. So when you will see the electronic configuration of, when you see the electronic, when you will see the electronic configuration of Be in ground state, it will be 2s2 and 2p is empty. As you can see, it is nothing is here, right? So what will happen when it will be go in the excited state? It will, the one electron will jump from here to this orbital, right? So as you can see, it is jumping from here to here. So at the time we have got what? One we have got in 2s, in 2s, one we have got electron in 2s, and one electron we have got in 2p, right? One electron we have got in 2p. So as you can see here, right? So now what will happen? Be atom, what it will do, it will accept two electron, right, to form BeH2. So what will happen? As you can see, as you can see here, it will accept one electron in this 2s and one electron in 2p, and this way it will form sp hybridization, right, like this. As we have already talked about this, right? It will form like this, right? As you can see here. Now here, these two sp hybrid orbital of Be overlap axially, okay. This is called what? Axial, because it is overlapping, this position is called axial position, right? It is overlapping axially with 1s orbital of two hydrogen atom, okay, to form what? Two sigma bond. Here whatever the bond which is formed in BeH2, it will be, this bond is what? Sigma bond, right? Here the bond which is formed is sigma bond, right? And the shape, when we talk about the shape, it is a linear shape, and the bond angle, regular bond angle will be 180, right? So I hope you have understood this, right? As you can see the shape, here 1s of hydrogen and 1s of this p, 2s of this p will combine like this. Here you can see it is combining like this, and the bond angle between this and this will be 180, right? So I hope you have understood this, right? Now next is CO2 molecules. So in this CO2 molecules, here carbon has two sp hybrid orbital, okay. Carbon has what? Two sp hybrid orbital, okay, and two unhybrid p orbital. So unhybrid will form what? Pi bond, I have already told you, right? And the hybrid orbital will form sigma bond, right? Now it shows that it's, when you will see the shape, it will have a linear in shape, okay, linear in shape with 180 degree bond angle. As you can see here, it is given. Okay, this one is what, the one which is forming a pi bond here, this one, right? This one, the one which is forming a pi bond here, this one, or this one, this is what, unhybrid orbital. But here the bond which is formed here and here, it is called, it is formed due to hybrid orbital. Okay, and this pi bond is formed due to unhybrid orbital, and this here and this it is formed due to hybrid orbital. Okay, so here you can see oxygen bond, O bond is reduced due to the presence of pi bond. Okay, and the bond angle between carbon and oxygen, as you can see, the when we will see the bond angle between carbon and oxygen, it will be reduced because of the presence of pi bond. Okay, now next is, as you can see, one more example is given here, CH double triple bond CH, right? So here in this case, each carbon atom contains two sp hybrid orbital. Okay, and two unhybrid p orbitals. Always remember that the two unhybrid p orbital will form a pi bond, and the sp orbital, every sp hybrid orbital will form a sigma bond. Okay, so as you can see, in the ground state the electronic configuration is this, as you can see here, but when it will be in the excited state, its electronic configuration will be this. Okay, and the carbon, what it will do, it will accept 4 electrons from hydrogen and 1 from carbon. Okay, as you can see here, right? So now here what we have seen, that in sp hybrid orbital of carbon overlap, overlap to give what, sigma bond, with what I have already told you. Okay, and the remaining one sp hybrid orbital of each carbon atom overlap with the s orbital of hydrogen. Okay, forming sigma bond within carbon and hydrogen. Okay, and the two unhybrid orbital, which is py on px, it will literally sideways, there will be a sidewise overlapping, and it will form pi bond, right? So as you can see here, so therefore what we can say, in carbon hydrogen, and here carbon hydrogen, what we can say, sigma bond between carbon A and carbon B, the bond, suppose this is a sigma bond, this is a carbon A and this is carbon B, so the sigma bond, suppose this is a sigma bond, is formed sp and sp overlapping. A sigma bond is forming, it is forming because of sp and sp overlapping, right? Now next is the sigma bond between Ca, this one, and this hydrogen here, this bond, when we're talking about this bond, let me draw it clearly. Suppose this is carbon here, 1 2 3, here hydrogen, sorry, suppose this is carbon 1 2 and 3, and here again one carbon, here hydrogen, and here is again one hydrogen. So always remember that. Now next one, what we are talking, the sigma bond between carbon and this hydrogen, this bond, when we're talking about this bond, this is formed between, because of the overlapping of sp here and s orbital of this hydrogen, right? And now here again, when we are talking about this, Ca is this, right? This bond, again this s orbital of this and sp hybrid orbital of this, right? They will overlap to form this sigma bond. Now next is pi bond of Ca and Cb. The pi bond, this bond and this bond, when we talk about this, is formed by the py and px. It is formed between by py and px overlapping, right? Now again, when we, what we can see, each carbon atom formed 2 sigma bond, but in C2H2 3 sigma bond is formed, as you can see. But when in here you will see that each carbon atom form 2 sigma bond, right? One with this, one with this, and one with this, right? One with this and one with this. But when we talk about the C2H2, here 3 sigma bond is formed, right? So this was about the sp hybridization. As you can see, one example is given here. This is formed, this one, this bond is formed because of the overlapping of sigma sp and sp. Okay, and this one is formed between pp and py, and pi bond which is formed between px and py, and this one is also with one s, for s is here, for this s here, and for this sp, and for this sp, right? So I hope you have got some idea about the sp hybridization. Okay, and when we talk about the type of molecules, what I have told you, the type of molecules will be AB, AB2, or AB, right? So some of the example you can take, the example of BeCl2, Okay, you can take the example of BeF2. Okay, all alkenes, whatever the alkenes is there. After that C3O2, you can take the example. After that allenes, you can take the example of allene and CO2 we have seen, right? So these are some of the example of sp hybrid orbitation, sp hybridization. Okay, now again, always remember that when you are talking about the molecule type ABX, okay, so here X is what it is representing the sigma bond. Okay, sigma bond pair, sigma, sorry, it is representing the sigma bond pair. Okay, and this A is what, here A is central atom. Okay, and here this B is what, this is side atom. Okay, so I hope you have understood this, right? Now next is sp2 hybridization. Okay, so this, when you talk about the sp2 hybridization, so here what will happen, let me draw it here first after that. So here 2s, 2s, suppose this is 2s here, this 2s. Okay, and this will combine with any two of the either px or py, or px or pz, or py or pz. Okay, suppose this is px to px. Okay, or suppose this is to py, or suppose this is to pz. Okay, so it will combine with any of the three. Either it will combine with 1s, will combine with this two, or 1s will combine with this two, or 1s it will combine with this two. Okay, to form what, sp2 hybridization. Okay, so when it will form hybrid orbitals with s px y to xy, at that time the empty orbital will be pz. Okay, right, at that time the empty orbital will be pz. If it is forming sp2 between yz, at that time the empty orbital will be what, px, right? And if it is forming with spzx, so at that time the empty orbital will be py, right? So now I hope you have got some idea. Now next is here one s orbital and two p orbital will intermix. Okay, and when you will talk about the percentage of characters, here 33% will be s character. Okay, and 67 will be 67, approximately 67% will be p character. Okay, and when we talk about the geometry, his geometry will be trigonal planar. Okay, and regular bond angle will be 120. Okay, so we will see this here in sp2 hybridization, intermixing of 1s, as you can see, and 2p orbital to give 3 sp2 hybrid orbitals. Okay, is called what, sp2 hybridization. As you can see, 1s is combining with either 2px, 2py to form this, right, sp2 hybridization. Now next is here 3 sp2 hybrid orbital lies in a same plane. Okay, directed towards the corner of a equilateral triangle with which is 1 and 120 bond angle between them, right? And the sp hybrid orbital, so 33% of s character, we have talked about this, and 60% of p character. Okay, so one example is given here, we will see only one example. So here example of bf3 is given. As you can see, in BF3 molecules, central atom is what? B, right? And its electronic configuration in the ground state will be this. As you can see, 1s2, 2s2, and 2p1. But when in the excited state, it will be 2 in s. One will say one electron will shift from here to here, as you can see here, right? Now next is what will happen. B atom will accept 3 electron, right? One in this orbital, another one will be in this orbital, and the third one will be in this orbital, right? As you can see, in one here, one here, and one here. So what they have formed, it is means what, here you can see what they are using in for the formation of bf3, 2p orbital are using, right? 2p orbital is used and 1s orbital is used. That is why it is written sp2 orbitals, right? Because 2p orbital, 2p orbital, and 1s orbital. That is why it is written sp2 hybrid orbitals, right? So I hope you have understood this, right? Now next is what, 1s orbital and 2p orbital of b atom intermix to form what, 3 sp2 hybrid orbitals. sp2 hybrid orbital, right? And these three hybrid orbitals orient in a space of planar triangular manner with a bond angle 120. As you can see here, it will be like this, right? So this is called what? This is called what? Planar triangular shape, right? So I hope you have understood this, right? So some of the example, one more example is written here, given here. As you can see, the example of C2H4 is given. Okay, and now we will talk about the sp3 hybrid orbital. So in sp3 hybrid orbital, always remember that 1s, okay, and 3p, okay, 1s and 3p. One is this, suppose one is this and another one is this. So the three will combine to form sp3 hybridization, which will be like this, something like this. Okay, sp3 hybridization. Here 1 2s, when we talk about the 2s, okay, and here 2p will be like this. Suppose one is this, one here, okay, 2p. So it will form 2s like this, okay, and 2p will be like this, 1 2 and 3, 1 2 and 3, right? So in this way they will combine together to form sp3. Let me draw it again here. They will combine to form sp3, which we can write like this, 2 3, 1 2 3 4, means here 1 is s and 3 is p. This 3 is p and this one is s, so it will be like this, 1 2 3 and 4. Okay, so what is the basic, what we can say here, 1s and 3p are intermixing. Okay, when we will see the percentage of s and p character, here you will see that s character is 25% and p character is 75%. Okay, and the shape will be tetrahedral shape. Okay, and the regular bond angle will be approximately 109.5 degree. Okay, and some of the example we will see that. Okay, so now we will see here. So sp3 hybridization is an intermixing of 1s and 3p orbital to form what? 4 sp3 hybrid orbital is called what? sp3 hybridization. Okay, now formed hybrid orbital oriented in tetrahedral manner, as I have already told you, with a bond angle of approximately 109 degree and 28 minutes. Okay, and sp3 hybrid orbital, so 50%, sorry, it is not, it will not be 50%, it is something mistake is there. Okay, make it correct in here. So here s character will be 25% and p character will be 75%. Okay, now as you can see here, so one example you will see, example of ch4. So we know that here central atom is carbon, right, and the side atom is hydrogen. So carbon has an electronic configuration, as you can see, 1s2 2s2 2px1 2py1 and 2pz is 0. So this is the ground state. As you can see, the electronic configuration in the ground state is this, right? Now again, when you will see the excited state, what will happen? One electron will jump from here to this, right? So it will be like this, right? So what will happen here? You can see carbon, what it will do, it will accept 4 hydrogen, right? So one in this, one in this, another one in this, and this one in this, right? So as you can see here, it is accepting one electron in each. So when you will see here 3 p orbital are using, right? We are using p orbital here 3, right? And how many s orbital? 1. So that is why it is written sp3, right? So some more thing we will see about this. As you can see here, 1 s orbital and 3 p orbital of carbon atom intermix to form what? 4 sp3 hybrid orbitals, right? And these hybrid orbital orient in a space of tetrahedrally with a bond angle of 109 and 28 minutes, right? So as you can see here, one is this, 2 3 4, right? And the bond angle is 109.5 degrees, right? So as you can see here, when we talk about the bond, all are sigma bond. This is forming a sigma bond here, he is forming a sigma bond here, here also sigma bond, and here also sigma bond. Okay, so I hope you have understood about the sp3 hybrid orbital. And one more thing that which is important for you, always remember that in organic compound, whenever carbon form 4 sigma bond and 0 pi bond, it is called sp3 hybridization. Always remember that, right? And the next is when carbon form 1 pi bond and 2, it will be sp2 hybridization, and when it will form 2 pi bond, it will be sp hybridization. Okay, so I hope you have understood this, right? So there is an example of NH3 is also given here. As you can see, example of H2O, they are all tetrahedral, and they are all, as you can see, some of the example, they are all in a tetrahedral manner. They are arranged in a tetrahedral manner, H2O. Now next is, after this we will see sp3d. Now before starting sp3d, I will give you the example of sp3. The example of sp3 will be CH4 SO4 ClO4, okay, H2O, we have seen H2O, NH3, okay, SiO2. These are all the example of this sp3 hybridization. Okay, now we will see sp3d hybridization. Sp3d hybridization. Okay, so in sp3d hybridization, we will see that here will be one. Okay, before starting sp3d hybridization, I will give you one introduction about this. Wait. 3s and 3p orbital, right? So quite often d orbital, what it will do, it will also get involved in the bonding process. Okay, now the paired electron in the 3s and 3p orbital can be promoted sometime to the vacant d orbital. Okay, and thereby making the hybridization possible. Okay, that is why it is forming sp3d orbital. Okay, so when we talk about this sp3d hybridization, so here you will see that there is one 3s, okay, and one 3px, one 3px, okay, 3px, this is along this direction, and one is 3py, like this, along this direction, okay, 3py, okay, and one is along z axis, okay, you can say 3pz, okay, and another one is dz square. So dz square, when you will see the how we used to represent this, we will represent like this. Okay, we represent like this. Used to represent like this. Okay, so this is what here, this is along z, okay, and this is y, and this is x. Okay, so this is what, there is a dz square orbital. Okay, so in this way they will combine. So they, when they will combine, they will form like this, which will be like this. Like this they will form. Okay, in which this 1 2 3 and 4 will be in a plane. Okay, as we will discuss about this. Okay, so one more thing before starting this, if d is form the same as s and p, then we write sp sp3d. Okay, when if d is from same s and p, okay, same s and p, then we write sp3d. Okay, now sp3d orbital or hybrid orbital having a trigonal bipyramidal geometry. They will have a what? Diagonal bipyramidal geometry. Okay, so how it is formed, it will be formed between 1s, okay, plus 2px plus py, okay, plus pz, sorry, plus pz, okay, plus dz square. So when you will see the shape, its shape will be like this. Shape will be like this. Okay, its shape will be like this. This is called axial position, this is called axial position, this is called equatorial position, this is called equatorial position, and this is called equatorial position. So this type of shape is called what? This type of shape is called what? Trigonal bipyramidal shape. Okay, so I hope you have understood this, right? So now we will see from here. So as you can see, when we talk about the sp3 hybridization, here one s orbital and 3 p orbital and 1 d orbital are mixing to get what? 5 new hybrid orbital, which are equivalent in shape and energy as an sp3d hybrid orbital. Okay, now out of which, out of this 5 hybrid orbital, what I have told you, out of this 5 hybrid orbital, 3 hybrid orbital will be 180 120 and will be at 120-degree angle, okay, present on a plane, and a 2 hybrid orbital is perpendicular to the plane, okay, and the shape of the molecule will be trigonal bipyramidal, as I have already told you, this angle like this, right? So this one and this one is perpendicular, right? And this one here, 1 2 and 3, when you will see the bond angle, it will be approximately 120. Okay, now as you can see, so many examples are there. Here 5 sigma bond is there and 0 lone pair of electron. This is called trigonal bipyramidal. So example is given here: BCA, PCl5, PF5, PCl5, PBr5, PCA, PL5. So one example is given, as you can see. So these three are in the same plane. These three are is called what? Equatorial position. This one, and this one is in the axial position, as you can see. Okay, now one more example is 4 sigma bond, and when there is 4 sigma bond and 1 pi bond, at that time the shape of the above example will be irregular tetrahedron. As you can see, this is called irregular tetrahedron. Okay, now again, when there will be a 3 sigma bond, so at that time it will be of T shape. Okay, so for this I will give you one very interesting example for this. Suppose when we talk about the sp3 hybridization, if the lone pair is 1, okay, so if the lone pair in sp3 sp3d hybridization, when we are talking about, when the lone pair is 1, at that time bond pair will be what? 4, right? And the molecule type will be a b 4, and one lone pair will be there, right? One lone pair will be here, right? So at that time, when you will see the shape, okay, or when we see the shape, so shape will be like this. Shape will be, let me draw here, shape will be like this. Okay, shape will be like this, and the geometry will be like this. Okay, geometry will be like this, right? So some of the example is called this example, and we have an example here. So this is the this is the example. Some of the example is for this type of, and there is a one lone pair is there. At that time example, we can take SF4, SeCl4, TeF4, and all, right? And BeCl4 positive. These are all example when there is a one lone pair in sp3d hybridization. Okay, so now next, when there will be 2 or 3 hybrid orbitals, okay, as you can see, 2 pi bond, okay, when there will be 2 pi bond, at that time there will be 3 sigma bond, right? And the molecule type will be a b3, okay, and here one lone pair and one lone pair will be here. At that time the shape will be same, okay, shape will not change, okay, but the geometry will change. Shape will be same as it was before, like this, but the geometry will change to like this. Lone pair will be like this, right? So in this way we can define this sp3d hybridization. Okay, now as you can see, some of the example is also given here. Some of the example is given here, right? 5 4 3. Now next is sp3d2 hybridization. So when we talk about the sp3d2 hybridization, here 2sp, it can be sp3d2 can be written as like this: sp plus p2d2. Okay, so this sp, there will be 2 in the axial position, and this 4 will be on equatorial position. Okay, these two will be these two sp will be in the equatorial position, axial position, and the 4 this p2 d2 will be on the equatorial position. I will give you a diagram of this. This diagram will be something like this. Okay, one here, another one is here, one will be like this, here, here, another will be here and here. As you can see, these two these two are in the axial position. The s1 s character, the one which is s and p will be in the equatorial axial position, and the rest p2 d2 will be in the equatorial position, as you can see here, right? So we will see in detail about this, and the shape it will be square bipyramidal. Okay, and because it has 8 faces and 6 corners. Okay, so when we talk about this sp3d2 hybridization, so here what will happen, the when you will see the shape, let me explain you from here, it will be good for you. As you can see here, sp3d2, one s orbital and 3 p orbital and 2 d orbitals are mixing to give what, a new hybrid orbital known as sp3d hybrid orbital. Okay, and the shape is what, as you can see, octahedral. The shape of the molecule obtained from the above 6 orbital will be symmetrical octahedral. Okay, and the angle between all the hybrid orbital will be 90 degree. Okay, an example is sf6 alf6 2 minus and icl5. These are some of the examples. As you can see, these 4 are in the equatorial position and these 2 are in the axial position, right, as I have already told you, right? So I hope you have understood this, right? So now we will see the one table which will make you more clear regarding this hybridization and shape. Okay, so let me okay, we will discuss about this table. Okay, now you see, when the hybridization is sp, okay, when the hybridization is sp, at that time the bond angle, regular bond angle, will be 180 and the shape of the molecule will be linear. Okay, some of the example is bef2 becl2 co2 sco2. These are some of the example, right? Now again, always remember that when there is sp2 hybridization, at that time there will be bond angle, regular bond angle will be 120, and the shape of the molecule or shape of the molecule will be triangular coplanar. Okay, and the example is bf3 bcl3 bh3 lcl3, right? Now next is when the shape is sp3, when the hybridization is sp3, at that time the bond angle is, regular bond angle will be 109 degree and 28 minute, and the shape will be tetrahedral, and these are some of the example. Now when there is sp3d, at that time the bond angle, regular bond angle is 120 and the shape will be triangular bipyramidal. Example of pcl5, pf5, sbcl5 we have seen, right? When it will be hybridization is sp3d2, at that time it will be 90 degree. Okay, bond angle and octahedral, as we have seen the example just now. When it is sp3d3, at that time the bond angle is 90 degree and 72 minutes, 90 degree or 72 degree, and it is will be pentagonal bipyramidal. Example is this if7. And when it will be dsp2, at the time 90 degree square planar, and these are some of the example, right? So here only up to sp3 they have discussed up to sp3d3, right? So one more is there, which is D3S and DSP2 hybridization. Okay, so we will, with these two will also we will see. I'll give you one example because it is not mentioned here in the notes. Okay, yes, it is not given here, so we will discuss about this also. Now next is what, when we talk about D3 D3S hybridization. So this is formed by 4S, 4S will be there, and 3DXY will be there, and after that 3DYZ will be there, and after that 3DZX will combine to form what, D3S hybrid orbital. Okay, and when you will see the shape will be something like this, somewhat like this shape will be there. Okay, and like this, like this shape will be there. So this is called what, D3s hybridization. Okay, and the example is what you can see, Mn. You can take the example of Mn. So Mn, when we talk, it is electronic configuration is 3d5 and 4s2, right? So in Mn7 plus, when we talk about the Mn7 plus, it will be what, it will change, right? So this type of hybridization will form a molecule like this. As you can see, Mn, double bond O here, double bond O here, O here, okay, and here one single bond O, and here double bond O, sorry, double bond O. So as you can see, this forming a molecule like this, right? So this is what this was about D3s hybridization. Okay, and now next is last one is DSP2 hybridization. DSP2 hybridization. Here dxy and x square y square plus s plus px plus py will combine to form this hybridization, and the shape will be something like this. The shape will be somewhat like this. Okay, shape will be somewhat like this. Shape will be there, 2 3 and 4. Okay, or you can take the one very famous example. You can take the example of nickel. Here it will be like this, Cn minus, here Cn minus, here Cn minus, Cn minus, and here Cn minus. Okay, so you can take this example. This is also called what, DsP2 hybridization. Here you will see that in this type of hybridization, one s and two p orbital belonging to nth orbit, okay, and the one d orbital, which is x square and y square, dx square y square, belonging to n minus 1 hybrid orbital. Okay, and the energy level of the hybrid to form what, 4s and dsp2 hybrid orbital, and these four hybrid orbitals are oriented towards the four corner of the square, as I have already shown you, in the xy plane. Okay, and hence it is called what, square planar hybridization, right? And the last one is sp3d3. Sorry, and yes, sp3d3. So when we talk about the sp3d3, so here it is also called pentagonal bipyramidal hybridization, and here we know that one ns orbit, okay, and 3 np orbit, okay, and 3 nd orbit, okay, and will hybridize to form 7 sp3d3 hybrid orbitals, okay, are formed, and the hybrid orbital obtained are oriented along the seven corner of the pentagonal, okay, bipyramidal. In the example of if6 is the example of this sp3d3. I will draw here, right? sp3d3, when you will see the example, it will be, suppose this is an I here, 1 2 3 4 5 6 and 7, and all the side there is f f f, here also f, here also f, here also f, and here also f. Okay, so I hope you have understood about the concept of hybridization. Okay, now we will see the method to predict the hybrid state of the central atom, because suppose we have given a central atom here, so we have to find out the hybridization. Okay, so always remember that we will see like this. If the value of x, as you can see here, it is again simple molecule. If it is a simple molecule, then we will use 1 by 2 plus v plus g valence, and v and g is what here. Here v is what, number of monovalent atoms, and g is number of outer valence shell or in a ground state. Okay, so here one method is given. One more method is there. If you are getting confused, I will give you one simple method, so from there you can easily protect. Yes, this method you can see here, when the value of x is 2, at the time sp3 is sp2, 4 is sp3, 5 is sp3d, and 6 is sp3d2, and 7 is sp3d3. Okay, so I will how to calculate this, I will give you one example. Suppose we have c2 and h2, okay, and we have to calculate the hybridization of the central atom. So how we will calculate? First step is what we have to do. The first step is we have to add the number of valence electron of all the atom present in the given molecule or ion. Okay, now next is when you talk about the second step, in each case of cation, okay, in each case of cation, we have to subtract the number of electrons equal to the charge on the cation, and in case of ion, we have to add the number of electron equal to the charge on anion. Okay, now in the third step, what we have to do, third step will be of two step. One will be if the result obtained in the second step is less 8 is 8 or less than 8, then we have to divide by 2 and to find the sum of the question and the remainder. Okay, now if in the second case, if the result obtained in the second case is between 9 and 56, okay, then we have to divide it by 8 and we have to find the first question q1, and if any remainder r1 is left, we have to divide it by 2 and find the second question q2. Now what we have to do, now we have to add all the questions of the final remainder r2, and if q1 plus q2 plus r2, yeah, and if the value of x, the hybridization predicted, we will get the hybridization. Okay, so I hope you have we will understand why the when I will solve, right? So here suppose C2H2 is given. So first of all we have to find out the total valence electron. Okay, I am writing in a short form, right? Suppose we have here C2H2. So first we have to find out the total valence electron. So when we will find a total valence electron, it will be, for this we can write 2, and valence electron is for carbon is 4, right? And plus valence electron for hydrogen is 1. So what we can write here, 10, right? Now next is what we will find. I have told you we have to find q1 first. Okay, so when we will find q1, so it will be how much valence electron is 10, right? So if it is what I have told you, it is less than 8, it is 10, right? So we have to divide it by 8. Okay, we have to divide it by 8, and it is coming what, 1, right? And remainder we will get r1, we will get 2, right? Here r1 we are getting 2. Now next, because when you will divide 8 divided by 2 is what, 8 ones are 8, we will get remainder 2, right? As we have got here, remainder 2. Now after that we will find q2. So when we will find q2, we will get 2 divided by 2, because what we have done here, if the result obtained in the second step is 8 or less than 8, right? So divide it by 2. Since we are getting here 2 which is less than 8, so we will divide by 2. So when you will divide by 2, we will get 1 here. Okay, and r2 we will get what, 0, right? r2 is 0 because nothing is left here, right? So now in the hence what we will do, we will add this one. Which one we will add? This one and this one we will add, right? So when you will add x is equal to 1 plus 1, you will get here 2, right? So if there we are getting 2, means the hybridization is what, sp. I hope you have understood this, right? Now we will see one example in which there is we have to divide it with 8. Okay, one more example I will give you, in which we have to divide it with the 8. Suppose the example we are taking here PCl5. Okay, we are taking here the example, sorry, PCl5. So in PCl5, total valence electron is what, 5 plus 7 into 5, which is 40, right? So when you have to find q1 you will find it will be 40 divided by 8. Okay, we will get 5 here, and the remainder we will get here 0, right? And then x will be 5, so its hybridization will be sp3d, right? Now one more example. Right, one more example we'll see. Example of c sorry example of c2 and h4. Okay, so when you'll see the example of c2h4, total valence electron will be how much? It will be 8 plus 4, which will be 12, right? And q1 will be 12 by 8. Okay, and when you will divide it 12 by n, we will get r1 you will get here 1, and r1 you will get as r1 you will get 4, right? Now again, when you will divide, when we will find q2, at that time it will be 4 by 2, which will be 2. R2 we are getting 2, and sorry, r2 we are getting 0, right? So when you will find x will be what? X will be 1, this one, and plus 2, which we have got here 2, this one, this 2, so total is 3. So the hybridization is sp2, right? So in this way you can find out the hybridization. Okay, you can refer to your book also, and if not, you can refer here. Okay, here is all, one process is also given here. So from this two process you can find out, you can do any, you can take any, you can pick any process and you can calculate this, right? So I hope today you have understood about the hybridization. Okay, if you have any doubt, let me know in the comment section. Okay, till that, thank you.